Hello and welcome to this lecture. So now we are going to put together these ideas of range and null and study something called a fundamental theorem of linear transformations. Okay, so it gives you a very beautiful and elegant result relating the rank and nullity of a matrix or a linear transformation. In general, any linear transformation satisfies a very simple law relating the rank and nullity. Okay, so that's what we're going to see now. It's a little bit abstract. I will state it in slightly abstract terms without referring to coordinates and all that, because the proofs are easier in the abstract world. You'll see it's so elegant and nice. We'll do that. Even if you don't understand the proof, just be patient with the result, and the final result is very important to remember and understand. We'll see that rank nullity theorem or the fundamental theorem of linear transformation. So let's get started. It all starts with this very innocent looking lemma called linear dependence lemma. It's a very simple lemma. It seems very trivial in some sense when you see it, but it has powerful applications. Again, small results adding up to very big results, right? That's the essence of mathematics. Okay, so what is this lemma? It says if you have v1 to vn being a set of linearly dependent vectors, there is a structure to them. What is the structure? It turns out there is a j, some index j, such that vj, the jth vector, belongs to the span of all the vectors before it. Okay, so if somebody gives you n linearly dependent vectors, whatever they give you, it should happen that there is one index j such that vj, the jth vector, is in the span of only the vectors before it. Okay, right? Seems like a simple result. You'll see the proof is also very easy. Okay, and since vj is in the span of v1 to vj minus 1, I can drop vj and my overall span will not change. Span of v1 to vn and span of v1 to vj minus 1 without the vj, right? It will be the same because vj is in the span. So if we take this span, I will get it. So the span is enough, right? So the second part I won't prove. The first part I'll prove. You'll see the proof is really easy. So what does it mean to say v1 to vn are linearly dependent? There are scalars c1 to cn, not all 0, such that you have 0 as a linear combination. Now go through each of these cj and find the maximum index such that ci is not 0 and everything else after that is 0. Okay, so this will always exist. Worst case, maybe cn is this guy, right? Well, that's also okay, right? In any index is okay, but there may be an index before that, so that is the last non-zero guy. Everybody else is 0. So basically, j is the last non-zero index value, the scalar index value such that the scalar is non-zero. Okay, I hope that's clear. So that is j. So now once I have this, basically it means Cj is not 0 and everything else after that is 0. So what does that mean? If you go back and look at this guy, Cj is not 0 and everything else after that is 0. So my condition, linear dependence condition, basically becomes something like this. Now I can push this around, keep Cj is non-zero, push this to this side, keep everything else on that side, divide by Cj. I get Vj as a linear combination of v1 to vj minus 1, which means it belongs to the span of v1 to vj minus 1. Okay, very innocent looking result, very simple result, but you'll see its power as I use it to prove more and more significant results. So this is the linear dependence lemma. Okay, one thing you can show using the linear dependence lemma is come up with a very simple procedure to show that a spanning set always contains a basis. Basically, if somebody gives you a spanning set for a subspace, here is a spanning set for a subspace, I can drop specific vectors from it and end up in a basis for that same subspace. Okay, so some sort of a dependence removal procedure is there. Supposing you have v1 to vn, it's a spanning set for this subspace, yes, but maybe some of these are dependent on each other, right? If I want a basis, I need a linearly independent spanning set. So there is a procedure using the dependence lemma to remove dependence and end up with a basis, which is a subset of this spanning set. Just drop a few vectors and you get a spanning set. Which one do you drop and you get a basis from the spanning set? If you drop a few vectors, you get a basis. So what are these vectors you have to drop? That is this dependence removal procedure. Okay, again a very easy procedure, but you will see if you use it powerfully, you can get very non-trivial result. Okay, here is the procedure. So sort of an obvious procedure. You start by defining a set B, which is all these vectors v1 to vn. And then you do a loop. What is my loop? J goes from 1 to n, and for every j, I will check if this is true. Does vj belong to the span of all the previous guys? If yes, I will delete vj from b. Okay, I will reduce 1 by b. Otherwise, I won't do anything and continue. When I end, it turns out I would have removed all the dependencies. Okay, I can output B as a basis for S. Why? Again, just the linear dependence lemma, right? In B, in the final B that I put out, there is no Vj which belongs to the span of the previous guys. Now, that means according to the dependence lemma, my V1 to my B is linearly independent, right? If it's linearly dependent, it has to have a Vj like that. I've removed all the Vj's like that. So this is the case. In fact, this procedure may look a little different to you, but it's actually only a minor variation of elimination. It's sort of similar to elimination in spirit. Okay, so this output is a basis for S. It has only linearly independent guys, and it also spans the same set as the original one. So this dependence removal procedure is very powerful. It gives you a basis from the spanning set just by dropping linearly dependent vectors from the list very carefully. Okay. So this gives you another very powerful idea. If you have a basis for a subspace, you can add vectors to it to get a basis for the entire vector space. Okay, so how does that happen? This is how it happens. Let's say you have Fn and there is a subspace S here, and there is a basis for the subspace u1 to uk, and this k has to be less than or equal to n, right? It turns out you can keep u1 to uk as it is and add n minus k other vectors. Okay, n minus k other vectors from Fn to create a basis for the Fn. Okay, so basis for Fn needs n vectors, right? You have only k vectors here. These are linearly independent. They span only S. Okay, I need to add n minus k other guys such that I don't compromise the linear independence, but I can span the entire Fn. So that's the nature of this problem. It turns out you can use our wonderful ideas of linear dependence lemma and the dependence removal procedure to get this done. Okay. Seems a little odd. How do you do it? Here is how you do it. You start with any basis for Fn, okay, v1 to vn. It can be any basis, but if you want to be specific, you can take this to be the canonical basis, right, e1 to en. So let's say v1 to vn, any basis for Fn. And here is what I do. I'm going to use the dependence removal procedure on a very specially constructed spanning set for Fn. What is this very specially constructed spanning set for Fn? This guy. My spanning set has k plus n vectors, okay, a very big set to start with. I know for sure that it will span the entire Fn, right? It's got u1 to uk and then v1 to vn is also there. v1 to vn itself will span. If I throw in more guys, of course the span cannot go down, right? So this entire thing spans Fn, but it has a very nice sequence. It starts from u1 to uk and then goes v1 to vn, okay? I'm going to now use dependence removal procedure on this spanning set. Okay. If I use dependence removal procedure, I have my loop variable j, right? My loop is going j equals 1 to k, and then it will go to k plus 1, k plus 2, all the way till k plus n. There are k plus n vectors in the spanning set. So my dependence removal procedure will loop over this, guys. J was my loop variable. It goes 1, 2, k, etc. Now what will happen when I run this loop? Here is an interesting observation. Till k, okay, up to k, no vector can be removed in my disposal removal procedure. Why? Because u1 to uk are already linearly independent. So no way uk will belong to the span of the previous guys. uk minus 1 will not belong to the span of previous. None of these guys will belong to the span of the previous guys because they are all linearly independent. Okay. So u1 to uk are linearly independent. Nothing in u1 to uk will be removed according to my dependence removal procedure. So if I didn't remove anything for the first k, what should happen in the remaining n? From k plus 1 to k plus n, you have to remove k vectors. You will remove k vectors. I don't know what it is, but you will remove k vectors and n minus k will be retained. Because finally you have to get a basis for Fn, right? This is a spanning set for Fn. My disposal removal, dependence removal procedure will give me a basis, and that basis has to have only n vectors. It cannot have more than n vectors, right? That's what I know about basis, right? So from k plus 1 to k plus n, it will remove exactly k guys and keep n minus k guys to give you a basis, which will be u1 to uk, comma, some vj1 to vjn minus k. I don't know what positions these will be, but they will be exactly n minus k of them, and all of them together will form a basis for Fn. Okay, so how beautiful and elegant and simple, right? We went to the abstract side and see how easily we are able to talk about these kind of results without reference to any coordinates or anything like that. Okay, so any basis of any subspace can be extended to a basis of the entire vector space and that is a powerful result. Now, all these things we are going to put together and learn more about our linear transformation. See, ultimately our goal was to learn a little bit more about our linear transformation, right? Null, range, what is it actually doing? If you use all these results, you can say something very wonderful and clear about linear transformation, and that is related to the fundamental theorem of linear transformation. So, this is what it is, okay. You have a linear transform T from Fn to Fm, okay. So, Fn to Fm, I have a null T, and null takes me to 0 in the Fm. And then I have a range T, range is basically entire Fn comes here. I am not showing that line, but entire Fm comes here. The fundamental theorem says rank of T, which is the dimension of range of T, if you add it to nullity of T, which is the dimension of null of T, has to be equal to n, which is the dimension of the original vector space we started with for any linear transformation T, okay. On the face of it, this may seem a little surprising to you, right. So, T is of course a linear transformation from Fn to Fm. It is a very strongly structured object. It is not like anything you can pick. It is a very strongly structured object, and it results in that T results in a range of T, which is a subspace of Fm, and it also results in a null of T, which is a subspace of Fn. These two are specially defined, and they are defined in some way, and they are subspaces. We know they are subspaces, they have dimension, but these two dimensions always, whatever T may be, these two dimensions always have to add to n. So, in particular, for instance, if this null space has dimension 0, right, if null space has dimension 0, as in only the origin goes to the origin, okay, then what should happen to the rank of T? Rank of T will become n, right, because nullity of T is 0. So, look at the applications here. This theorem has very many applications. So, if null space null of T is 0, right, nothing other than the origin is there, then rank of T has to be n. But now rank of T is a dimension of a subspace of Fm, which means this m has to be greater than or equal to n, right. So, if you want null space to be 0 only, then this m has to be greater than or equal to n, otherwise null will be something non-trivial, okay. So, just with this result, you can come up with very nice interpretations on just based on n and m, what null has to be, what range has to be, you can come up with in a very, very nice way, okay. I hope you see this power of this, a lot of powerful ways in which questions can be asked. I hope you have such questions in your assignments, okay. So, we are going to try and prove it, and the proof will use all the previous properties that we had. I am going to quickly walk you through the proof. Even if you do not follow the proof in the first time, it is okay, try to look at it. It is a little bit abstract, but hopefully you will see the point of it, okay. So, we are going to assume first nullity of k, T is some k, okay, any k, and let us say the basis is u1 to uk, okay. Now, I have a basis for a subspace of Fn. What I am going to do is extend. I will extend this basis u1 uk to a basis of Fn. Let us say that will be w1 to wn minus k, right. There will be n minus k additional basis vectors that I will get. So, that with k plus n minus k, I have n things, and this entire thing is a basis for Fn, right. So, this is the same procedure that I had before. I had different notation for these w's, I am just changing them to simple notation. Now, here is the proof. The interesting claim of the proof is the following. If you take this w1 to wn minus k and you hit them with t, okay, if you hit them with t, what will happen? I will get t of w1. Now, that will have to be inside the range, right, and I will hit t of w2, that will also have to be inside the range, t of wn minus k, that will also have to be inside the range. All these guys have to be inside the range, and it turns out these guys, t of w1 to t of wn minus k, form a basis for range T. So, basis meaning they have to be linearly independent and they have to span the entire range of T. Now, this proof, I am not going to do it, I will leave it as an exercise. If you can figure out a proof, please post it on the forum for everybody's benefit. It is actually a very elegant and clean proof, and this is the crux of the thing. So, this tells you wonderfully about the structure of T, right. Not only do you know about null and range, so when you take a basis for null and extend it to a basis for Fn, take the extension vectors and map them with T, what you get is a basis for range T, okay. So, it is a powerful result, and this in particular gives you this rank nullity theorem, but there are also other ways in which you can use it. It really gives you a comprehensive idea of what your linear transformation is doing, right. It takes every null, the entire null, and puts it to 0, and it takes the other extensions and takes it to a basis, and this is a very clean way to understand a linear transformation. So, once you have this result, everything is easy, right? Once we know that this is a basis, dimension is just n minus k, dimension of range of t plus dimension of null of t is n minus k plus k, which is n, and that is the proof of this theorem. Okay, so only thing I have left out is this proof for this basis for age t. It is not really very hard. I will invite you to try it and post it on the forum if you find a proof, or you can look for the proof in some place or the other. Okay. So, that brings us finally to our example. You can check the fundamental theorem. You found the null space dimension, you found the rank, and you can check out everything in the fundamental theorem, right. So, you take the basis for the null, extend it, and do with the t and see if you are getting a basis for the range, and play around with it and learn from it. It will be a wonderful experience. Okay. Thank you very much.